Hello guys, so for this video we're going to look at an example to see how we can find the stationary values of multivariable functions. In this case we're going to focus on two variable functions. So let's first of all get over with the idea of, or basically the conditions of finding the critical points. So to find critical points, we know that we need to equate df by dx, which is the partial derivative of f with respect to x, to 0, and also equate df by dy, which is the partial derivative of f with respect to y, to 0. And hence, doing this will give us the critical points. Now, what do we do to analyze these critical points, as in decide if these critical points are either a maxima, minima, or a saddle point? So for that, we have the following conditions, where we get a minima if the second derivative, the second partial derivative of both of the function in terms of both x and y, which is, as you can see over here, d squared f by dx squared and d squared f by dx squared is positive, and also df by dx dy squared, which is the partial derivative twice in respect with x and y squared, is less than the multiplication of the second derivatives, which is d squared f by dx squared multiplied by d squared f by dy squared. If these conditions are met, then we get a minima, and we get a maxima if d sorry so if d squared f by dx squared and d squared f by dy squared is negative, and the same condition where we had the partial derivative of f with respect to x and y squared to be less than d squared f by dx squared multiplied by d squared f by dy squared. If these conditions are met, then and only then we get a maxima. And the third point, or the third category of critical points, is the saddle point. And we get the saddle point if d squared by dx squared and d squared f by dy squared have opposite signs, meaning that if d squared f by dx squared is positive, then d squared f by dy squared is negative, and vice versa. And also d squared f by also df by dx dy whole squared is greater than the accumulated multiplication of d squared f by dx squared with d squared f by dy squared. Now these are the following conditions that we have to look for to analyze the behavior of the critical point, or how in fact the critical points are. So to see that, let's make a little bit of space and look at an example. So the question that we're going to look at is find and classify, meaning we have to analyze the critical points, all the critical points of the function. Now the function is given as f of xy. We can see from here that this is represented by two variables, which is x and y, and the function is 4 plus x cubed plus y cubed minus 3xy. So we need to find a few things. We see that from the conditions, the things that we need to find is df by dx to find the critical points by equating it to 0, and also df by dy, because we need to equate both of these to find the critical points. And also we need to find the second derivatives, the second partial derivatives with respect to x and y both. And we also need to find df by dx dy, which is the partial derivative of f with respect to x and y. So now again, these can be written as fx, fy, fxx, because we're differentiating it twice with respect to x, fyy, and this is fx. fxy. Now you see that fxy and fyx is the same thing, so we don't need to find that twice. We can just find fxy or fyx if that's simpler. So we're going to find fxy. So now what we're going to do is to find the critical point, first equate both of the first partial derivatives, which are these two, to 0. Now fx from the given function over here, you can see that fx will simply be 3x squared minus 3y, and to find the critical points we have to equate it to 0, and fy will also be 3y squared minus 3x, and again equating it to 0 to find the critical points. Let's call this equation 1 and let's call this equation 2. Now you see that we have two equations, and now we can solve them simultaneously to find x and y. So you see that if we solve the first equation, we get 3x squared equals to 3y, and then that gives us the relationship x squared equals to y, or simply y equals to x squared. Now we can put this relationship in the second equation, and substituting this into the second equation gives us 3x squared minus 3x equals to 0. This is simply 3x x cubed minus 1 equals to 0. Now this gives us two values of x, which is x equals to 0 and x equals to 1. Now at these points where x equals to 0 and x equals to 1, the critical points that we get using the relationship that we found before, which is y equals to x squared, we see that the critical points are 0, 0 and 1, 1. When x equals to 0, y equals to 0, obviously because we put x equals to 0 over here, and when x equals to 1, we also get y equals to 1. Now the critical points are these two coordinates over here, and we're going to analyze if these critical points are a maximum, minimum, or a saddle point. Now, analyzing these critical points, let's make a little space over here. So we know that for analysis, we need to find the following, which is the second derivative of the function with respect to x. So this is simply basically the derivative of the first partial derivative with respect to x in terms of x. So now this will become 6x, and then again we need to find fyy, which is basically the differentiation of the first partial derivative with respect to y. Now this simply becomes 6y, and we know that fxy is simply the first partial derivative of f of x with y, and this is minus 3. Now let's consider the first critical point. So critical point 1, which is 0, 0. So at this critical point, we see that fxx is 0, because you put the value of x over here, you get 0, and also fyy is also 0 because you put the value of y, which is 0, and you get a 0. And we see that fxy squared is negative 3 squared. This is positive 3. So according to the conditions that I've listed above, you see that fxy squared is in fact greater than the accumulated multiplication of f of xx and f of y. So since this is greater, then we know that this will be our saddle point. Now moving at the critical point 2, which is 1, 1, we see that f of xx is 6, putting x equals to 1 over here, and similarly f of yy is also 6, and f of xy whole squared is negative 3 squared, which equals to 2, which equals to positive 3. So from here you see that f of xy whole squared is in fact less than the accumulated multiplication of f of x with f of y, which will give us 6 into 6, which is 36. Now, so you see that this is less than, and this is one of the conditions. We also have to see that f of xx and f of yy is both positive. So in that case, culminating to the conditions that I've written down earlier, this will be a relative minimum. So you see how we can use the above conditions. I'm going to show that again for your convenience. You see that these above conditions can be used to analyze the critical points at a given of a given function.